Yeah, that's recording. Okay. So Newton's method is all about finding exact roots. Okay. For example, if we say if we have this kind of equation, and if I ask you to find what is the x value that is making my function zero, what were you using? I mean, what command were you using? We were using solve command, isn't it? We used solve, PPA solve, and we were solving for x, and we have got that. But this is not useful for most of the times because that is not the approximate value we were looking at. That is why we use another method which is called Newton's method, which is kind of an iteration method. I mean, we use it over and over again to find until we get an approximate value. Okay, that is what we have. Now, imagine if I have an equation like that, all right? And we to find the exact x value where my function is zero, I first plot it. See that I plot with the interval 0 and 1, just like given the question. So that's my 0 and 1. That's my plot. Now look at this carefully.
Okay, I believe we've lost your screen sharing.
Oh, really? Oops. I'm sorry. Yeah, how about now?
Yeah, it's good. See it.
Yeah. Okay. So if okay, I'm gonna post that video, don't need to worry. If I have that equation and we are supposed to find all the x values that is making my function zero, I first plot in that into 0 and 1. So now look at this carefully. That is my zero line, and I have three intercepts. Do you see that? I have one there, I have one there, I have one. There are three intercepts. That means there are three x values that is making my function zero. So I need to find all those values. That is what I given there. So this code is going to give you, I mean, I'm not going to go deep into those theory, so I'm just looking at only the lab manual and everything is given on the code, so take some time to read it. So this code is going to find the exact x value by taking some approximate x value. Okay, so now if you look carefully, I have I have a 0 point there. I can take somewhere between 0.2 or 0.3, so let me change it. Let me take 0.2. So
Interrupt
let me
KK, but can everybody else see the screen right now? It says it's starting to share content, but I don't see anything quite yet.
Yeah, it says that too.
I think the internet might be a
let me
bit
see the
behind.
screen.
It tells us you're starting to share content, but we haven't seen it quite yet.
I see. Trying to share the entire screen. Yeah, how about now?
There it is. We can see it.
Now?
Mm-hmm.
Okay. Is it good now?
Yes.
Okay. So that's my plot, right? Now that's my intercept. 1, 2, and 3. Right? That's my three intercepts. Now let me assume that my exact x value was 0.2 right there. But it's not true, right? It's not exactly 2. We need to find the exact value closer to 2. So use that. So what I've assumed is, I've assumed that my x value is 0.2, which is not true. So, but this guy is going the exact answer at 0.2. Okay. So that is my answer. That means my x at my x is equal to 0.226, I have an exact solution which makes my f of x 0. You see that? So basically Newton's method is to find approximate x value that is making the function 0 or the exact root. Okay, so that's one method. I mean, that's just a basic idea. So the second method is iterations, one after the other, one after the other. So we use this code assuming that x1, I mean the first approximate value is 0.25. You can assume 0.2, that doesn't matter. So when I assume that my x is 0.25, I have so much error. I have error of 0.1. So if I keep using the same error over and over again, I have the exact value as 0.2278, which is almost there. Okay, I think you must have watched a YouTube video on this, so try to watch that and get a basic knowledge, and this is
There's
after
a
that you
really
can.
good one that's 7 parts, each one being about 8.
Yeah, go ahead, Travis.
Apologies, my headset died just there for a moment. But I
Yeah.
was sorry for interrupting. As I was saying, there was a really good 8-part YouTube video on it from
Okay.
this channel. It's really good. I would recommend it.
Okay. Okay. Let us post that link as well on the discussion forum so that others can use it.
Yeah, very good. I'll do so.
Yeah. So the next is Newton's method on autopilot. So what we have done so far is we typed all those one after the other. I mean, the iterations we have done is one after the other until we have got a suitable 0.2278. Right. So there is one code which stops at right moment. So this code is going to give you first 20 approximations. All right. So the digits 12 signifies 12 significant digits. If you count these digits, it's 12. Okay. And count is actually one after the other. So that is why it says count of one is equal to one. Then we start off assuming that x1 is 0.25. Right there. Now this is the for loop. The 19 here is going to give you 20 approximations. So imagine if you want 10 approximations, you just have to change it to 9 instead of 19. Okay, and the other code remains just the same. So if you want 20 approximations, you have 20 different 20 answers. But if you closely observe, 4 and 5 is almost the same. That means the rest of the other answers are not useful because we have a similar answer at the fifth entry. So that is what we have for this Newton's method on autopilot. Now, there is
Okay, I want
one
to ask.
alignment question. Yeah, yeah. Just give
Yeah,
me a
are
second.
you about to talk about that one on the paper being inaccurate? Because I tried using the one on the provided PDF, but it gave me errors.
Yeah, so you cannot copy and paste that. So use my code and you'll be good.
Yeah, I didn't copy and paste it. I typed it.
Yeah. So there's one question where you are asked to find 20 approximations or 30 approximations in that 50 decimal. No, there's no question. Okay, that's one thing. But we don't want to have all these entries because it's of no use, right? We just want these first six or first five because after that it's all the same. So we have to throw out all those things which are the same. So that means we have to limit our iterations. So that is why we use this command, deciding when to stop. So here, digits is going to give you 17 digits. We start off assuming x value as 0.25, and the error, we are allowing error of 0.002. See that? 0.226, 0.227, and rest of it is the same. So we are allowing an error of 0.002. Anything less than that, the code runs over and over again. Anything more than that, the code stops. Okay, use that code, and you would have an answer as 0.2277. So that means at my sixth trial, I have a similar kind of answer. That's where my code stops, and your answer is 0.227758. Right? So that's one type of code. Now, if you again look at our graph, we have two more intercepts to find. So far, we found x closer to zero point 0.2. Now we have to find x closer to 0.5 and x closer to zero point 0.7 to 0.8. That means we have two more intercepts to find. So what I've done is I've simply plugged f of 1 over 2. That means f at zero point 0.5. So if I plug f at 0.5, I directly have a 0. So that means my exact x value is 0.5, right? So if I plug x is equal to 0.5 there,
Mhm.
I have a 0. So that means that I don't need to do any Newton's method because I directly have a point 0 at x is equal to 0.5. And my next intercept is somewhere close to zero point 0.7 and zero point 0.8. So let me assume by taking my x as 0.75. And I'm going to use the same code that I used there. See that? Instead of 0.25, I've assumed 0.75. So if I use the same code by just changing my x value, I mean my initial x value, the answer turns out to be 0.7, 77224. Okay, so most of your assignment questions would be on this area, and that area, because these things it's going to take so much of time because you cannot know when to stop. You don't know where to stop, isn't it? If you use this method. So that is why we use either autopilot to just simply spit out 20 or 30 iterations. And if you don't want to spit out some trash, you are going to do this code that is deciding when to stop. Because this code directly gives you an answer. I mean, the consecutive answers are the same. When the consecutive answers are the same, this code stops and you have very few iterations with the right answer at the end. You get that?
Yeah. Oh, so when we do those questions, it's either we use autopilot or deciding where to stop, or do
Yes.
we?
Yes, those two only. Yeah.
Oh, so it's by our choice we can choose one of the two, or do we have to
The
use
three,
both?
really.
Yeah, one of the three. Yeah, one of the three. You can choose one of the three, but you just decide which one is easy. You have three different methods. One is this guy. Just run over and over again. For instead of now let me do x8. Now x8, oops, x8 is I'm going to use my x7. Run that. The error again reduces. See that?
Hmm.
For x7 I have so much error, and for x8 I have so much error, which is almost the same. So I know that I need to stop at x of 8, right? So that means I need to keep running. I need to enter over and over again. But autopilot doesn't do like that. The first autopilot, what it does is it's going to spit out 20 iterations, but it doesn't know when to stop. I mean, you are not specifying when to stop. I mean, you are specifying you need 20 approximations, but it's not going to stop even though if you have a right answer. And the second autopilot is going to stop when you have two consecutive same answers. So it's up to you that you decide which one is easy.
Oh, okay. So it doesn't. So it's fine if we choose one or the other when we do each of those questions.
Yes.
Oh, okay. Wow. Wow.
So at the end, you must only show that the exact root for that particular equation is so and so.
Okay. Solution. Oh, also, just a question about the putting all together. So in it,